Good day, everyone. I am Cherry Jane T. Ablaza. Together with me, my co-reporters, Ma'am Sheila Lane E. Marinay and Ma'am Darlene Joy B. Fagdanan. The outline of our report includes the history, process, breakthrough, and the implication in modern study. The topic assigned to us entitled Observing Polyblocking in Ultracold Fermionic Gases. So let's have an introduction first. So particles in the universe classify into two major categories based on their quantum mechanical spin, the fermions and bosons. Fermions are half-integer by spin such as -3/2, -1/2, +1/2, and +3/2. So fermions includes quarks and leptons. Quarks are elementary particles composed of protons and neutrons. The famous example of elementary lepton is the electron. So this is an atomic structure of a lithium atom. Inside the nucleus is the quarks, and quarks composed of protons and neutrons. So electron is an example of a lepton which is rotating in the orbital. The energy level composed of subshells, the SPDF. As you can see, the square represents an orbital. Kung makikita niyo dyan, ang S may isang orbital. Ang P may 3 orbital. Ang D, 5 orbital. At ang F may 7 orbital. And take note, 1 orbital can hold 2 electrons. Kaya ang S, 2 ang nakalagay dyan kasi sa isang orbital may 2 electron. Sa P naman, 3 orbital times 2 is 6. Sa D, 5 times 2 is 10. Sa F, 7 times 2 is 14. So, okay po? So, proceed naman tayo sa Pauli exclusion principle. In 1925, Wolfgang Pauli came up with the Pauli exclusion principle. It states that no two electrons having an identical set of quantum numbers can occupy the same state within a quantum system. It explains why individual electron orbitals in an atom can contain at most 2 electrons, one spin up and other spin down. So this is an example of a Pauli exclusion principle. No 2 electrons can have the same set of quantum numbers. The spin of the quantum numbers must be opposite. The electron spin up where ms is equal to +1/2 and electron spin down where ms is equal to -1/2. Okay, so tingnan natin dito sa example natin. Ang oxygen ay may 8 electron. So paano ba ang tamang pag-fill in ng spin? Sa oxygen, may 8 na electron. Kaya, ang electron configuration ay 1s2, 2s2, 2p4. Ang sabi sa Aufbau's principle, lower level must fill before filling the next level. At sa Hans rule naman, 1 electron at a time before pairing. So actually, pareho lang ang sinasabi nila. So 1s2 sa oxygen, unahin mo munang i-fill in bago mag-proceed sa next level. Ganun din sa 2s2. Sa 2p4, may 4 pa na electron na natira. So dahil 3 ang orbital dyan at isa lang sila ng energy level, unahin mo munang fill in lahat ng box bago mo lagyan ng pair. Tandaan po na sa Pauli exclusion principle, dapat opposite ang spin ng quantum numbers para ma-occupy nila ang same state ng isang quantum system. Okay, so now let's proceed to the history of the breakthrough. A manifestation of the Pauli exclusion principle in ultra-cold atomic gases has been spotted for the first time by 3 independent research groups, called polyblocking. The effect was first predicted 30 years ago. And of course, when fermionic atoms in a quantum gas are unable to make transitions to nearby quantum states. So in the 3 experiments, Pauli blocking reduced the ability of atoms to scatter light, making the gases more transparent. The Christian Sanner and colleagues at Gila in the US, Amita Deb and Niels Kigard at the University of Otago, and Wolfgang Kitterly and colleagues at the Massachusetts Institute of Technology in the US, for independently observing Pauli blocking in ultracold gases of fermionic atoms. So Pauli blocking occurs in such gases because the constituent atoms fill nearly all available lower energy quantum states, which prevents atoms from making small transitions to neighboring states. So this affects how light scatters from atoms in the gas, and all 3 teams observed that Pauli blocking increased the transparency of their gases as they were cooled. So physicists, including those in Kitterly's group, have developed magnetic and laser-based techniques to bring atoms down to ultra-cold temperatures. The limiting factor, he says, was density. So ngayon, punta na tayo sa process na ginawa ng team ni Kitterly. So may 3 process silang ginawa. So una, first laser, laser cooling. Second laser, for further squeezing. Third laser, for final check. Okay, so sa first laser for laser cooling, in their study, they used techniques they developed previously to first freeze a cloud of fermions, in this case, a special isotope of lithium atoms which has 3 electrons, 3 protons, and 3 neutrons. They froze a cloud of lithium atoms down to 20 microkelvins, which is about 1/100,000 the temperature of interstellar space. The second laser for further squeezing. Then, they used a tightly focused laser to squeeze the ultra-cold atoms to record densities, which reach about 1 quadrillion atoms per cubic centimeter. Then, third laser for final check. The researchers then shone another laser beam in the cloud, which they carefully calibrated so that its photons would not heat up the ultra-cold atoms or alter their density as the light passed through. Finally, they used a lens and camera to capture and count the photons that managed to scatter away, and they counting a few hundred photons. At progressively colder temperatures and higher densities, the atoms scattered less and less light. At their coldest, at around 20 microkelvin, the atoms were 38% dimmer, meaning they scattered 38% less light than less cold, less dense atoms. And Pauli blocking in general has been proven and essential for the stability of the world around us. According to Wolfgang Kitterly, John D. Arthur, professor of physics at MIT, what they observe is very special and simple form of Pauli blocking, which is that it prevents an atom from what all atoms would naturally do, and that is to scatter light. This is the first clear observation that this effect exists, and it shows a new phenomenon in physics. Okay, so for further explanation, let me show you a video.